Have you ever wondered why predicting the motion of just three celestial bodies is one of physics' greatest challenges? Welcome to the enigma of the three-body problem, a puzzle that has perplexed some of the greatest minds in science. Here's the conundrum. We can accurately predict the motion of two celestial bodies interacting under the influence of gravity. That's the two-body problem, and it's pretty much solved. But add just one more body into the mix, and suddenly, we're in murky waters. That's the three-body problem. This is not about merely tripling the calculations. No, it's about grappling with an exponential increase in complexity, as each body exerts gravitational influence on the others and vice versa, in a dance of cosmic proportions. So, why is this seemingly straightforward task so darn difficult? This seemingly simple query opens the door to a profound puzzle that has baffled scientists for centuries. Buckle up, because we're about to dive deep into the mystery of the three-body problem. Our story begins over 300 years ago, with Sir Isaac Newton. In the late 17th century, Newton revolutionized our understanding of the universe with his laws of motion and the universal law of gravitation. Through his groundbreaking work, he provided a mathematical framework that could predict the motion of two celestial bodies with astonishing accuracy. For instance, Newton could describe the Earth orbiting the Sun, or the Moon orbiting the Earth, with precision that had never before been achieved. However, when a third celestial body was introduced into this model, such as the Sun influencing the Moon's orbit around the Earth, the predictions faltered. Newton's equations, which so elegantly described the dance of two bodies through space, could not solve the more complex interactions of three bodies. This predicament came to be known as the three-body problem. The complexity arises because every object in space exerts a gravitational pull on every other object, and each interaction influences the next. In a two-body system, these interactions are predictable and cyclic, but add another body, and the system becomes chaotic and unpredictable. In response to Newton's limitations, other luminaries of science stepped forward. In the 18th century, mathematicians like Leonhard Euler and Joseph Louis Lagrange made significant strides. Euler discovered special solutions to the three-body problem under certain conditions, and Lagrange identified points in space, now known as Lagrange points, where a small object affected by two larger objects can remain in a stable position relative to the larger bodies. These contributions were profound, yet they represented special cases rather than a general solution. The quest for a comprehensive solution to the three-body problem continued to perplex the finest minds in mathematics and physics. Despite remarkable progress, the complete solution remained elusive, setting the stage for a centuries-old quest. The mystery of the three-body problem would challenge and inspire generations of scientists, each building on the work of the last, in the hope of unraveling one of the universe's most intricate puzzles. Why is the three-body problem so complex? Let's delve into the mathematical intricacies that make this an enigma wrapped in a cosmic riddle. At its core, the three-body problem is non-linear. This essentially means that the equations involved don't follow a straight line or a simple curve. Instead, they twist and turn unpredictably, making it incredibly challenging to solve. Imagine trying to navigate a maze that's constantly shifting and changing its layout. That's the kind of complexity we're dealing with. Now, non-linearity alone wouldn't be so bad if it weren't for the fact that it leads to chaotic systems. In the realm of mathematics, chaos doesn't imply a lack of order. Instead, it refers to systems where small changes in the starting conditions can lead to vastly different outcomes down the line. This is also known as sensitivity to initial conditions. Take weather prediction as an example. Meteorologists use complex mathematical models to forecast the weather. But even the slightest inaccuracies in the initial data, like the temperature or wind speed, can lead to wildly different forecasts. That's why it's so hard to predict the weather accurately more than a week in advance. The three-body problem is a chaotic system par excellence. Consider three celestial bodies, say the Earth, the Moon, and the Sun. The tiniest change in their initial positions or velocities can result in dramatically different trajectories. This means that, even with the most powerful supercomputers, we can't predict their motion accurately over long periods. And here's the kicker. Even if we could measure the initial conditions with perfect accuracy, quantum mechanics tells us that there's always an inherent uncertainty in the position and velocity of a particle. So, the unpredictability is baked into the very nature of the universe. This sensitivity to initial conditions is what makes predicting the motion of three celestial bodies so fascinating and frustrating. It's like a cosmic game of billiards with ever-changing rules, yet it's this very complexity that makes the three-body problem such an intriguing area of study. The quest for understanding continues. How have modern scientists tackled this age-old conundrum? As we move into the realm of modernity, computers play an increasingly vital role in the quest to make sense of the three-body problem. Through the power of simulation, scientists can now explore a multitude of scenarios that would have been unthinkable in the days of Newton or Poincaré. Imagine a supercomputer crunching numbers at a rate that would leave even the most accomplished mathematicians breathless. It's here in the whirring circuits and lines of code that we find the numerical methods that allow us to approximate solutions to the three-body problem. These methods, while not providing a neat, closed-form solution, offer a way to navigate the complexities of the problem and predict outcomes with a degree of accuracy. Yet, the three-body problem is not just a matter of brute computational force. Theoretical advancements have also shed light on why a general solution might be, in fact, impossible. Take for instance the KM theorem, a cornerstone of modern dynamical systems theory. Named after the mathematicians Kolmogorov, Arnold, and Moser, this theorem suggests that even slight perturbations can lead to drastically different outcomes in a system. It's a statement about the inherent unpredictability of the universe, and it's one of the reasons why the three-body problem remains so tantalizingly elusive. We can't forget the work of Henri Poincaré either. His groundbreaking research on the three-body problem at the turn of the 20th century laid the foundation for what we now know as chaos theory. Poincaré showed that the paths of three bodies under mutual gravitational attraction can be chaotic, meaning they can't be predicted over long periods of time. So, where does that leave us? Despite the leaps and bounds made in computational power, and the theoretical advancements that have deepened our understanding of the problem, a definitive solution continues to elude us. In the face of the three-body problem, we are reminded that some mysteries of the universe may always remain just out of our grasp. Beyond the theoretical, what does the three-body problem mean for us today? Well, the ongoing research into this conundrum has significant practical implications, particularly in the realms of space exploration and astrophysics. For instance, space travel. The three-body problem helps us to map out complex gravitational fields, like those experienced by spacecraft journeying through the solar system. By understanding the gravitational interactions between Earth, the spacecraft, and the Moon or a planet, scientists can plot more efficient trajectories, saving precious fuel and time. Then, there's satellite deployment. Satellites, whether for communication, weather forecasting, or GPS, are an integral part of our modern world. But launching and maintaining these satellites in stable orbits requires a robust understanding of the three-body problem. It's a delicate dance of physics that keeps our digital world spinning. In the field of astrophysics, the three-body problem provides insights into complex orbital systems. It aids in the study of celestial bodies like planets, stars, and galaxies, and their intricate interactions. This understanding is crucial in predicting cosmic events and unraveling the mysteries of the universe. Moreover, these challenges spur technological and theoretical innovations. The quest to solve the three-body problem drives the development of powerful computational tools and stimulates advancements in mathematical theories. So while the three-body problem might seem like a purely academic exercise, it's a vital piece of the puzzle in our pursuit of knowledge and exploration. Thus, the quest to solve the three-body problem fuels cutting-edge advancements in multiple scientific fields. Is the three-body problem truly unsolvable, or does its mystery hold greater value? We've journeyed through the enigma of the three bodies, traversed historical horizons, unraveled complexities, and explored modern breakthroughs and limitations. Let's take a moment to reflect on these. The three-body problem, with its convoluted dance of celestial bodies, is a complex puzzle that has captivated thinkers for centuries. From Newton's time to our modern era, countless minds have grappled with its intricacies. Despite making significant strides in understanding, a universal solution remains elusive, a testament to the problem's profound complexity. But is this necessarily a bad thing? Perhaps not. Unsolvable problems like the three-body problem are far from being dead ends. Instead, they serve as powerful catalysts for scientific progress. They push us to the edge of our knowledge, nudging us to question, to probe deeper, to innovate. In the quest for answers, we've developed new mathematical tools, advanced our understanding of physics, and even sent spacecraft to distant worlds. The three-body problem, in its stubborn resistance to solution, has spurred us on a journey of discovery, a journey that continues to enrich our knowledge and shape our future. So, is the three-body problem truly unsolvable? Maybe, but does its mystery hold greater value? Absolutely. Perhaps the true value of the three-body problem lies not in its solution, but in the journey it compels us to undertake, a journey at the very frontier of human knowledge.